Good evening, everyone. We shall start this event by 3 p.m. Good evening, everyone. I am Akanshu, and I welcome you to the second lecture of the series Optics is not only about optics anymore by Professor Síle Chormaic. This lecture was originally scheduled on November 9, but because of some technical problems, we could not conduct this lecture. So, we again thank Professor Chormaic for agreeing to deliver his talk for the second time. Professor Síle Chormaic is a professor at Light Matter Interaction for Quantum Technologies Unit in Okinawa Institute of Science and Technology, Graduate University, Japan. She works in atomic and optical physics and is the PI of Neutral Atoms for Quantum Technologies Group, Nanobioptics Group, and Optical Cavities and Sensing Group. She is also honorable professor in University KwaZulu-Natal, South Africa. She has been in editorial board of Advanced Photonics since 2020. She is also a member of AIP, JSAP, and SPIE. Professor Chormaic received her PhD from University of Paris North, France for her work on Stern-Gerlach atom interferometry of hydrogen. She completed her postdoctoral studies in University of Innsbruck, Austria, and the University of Melbourne, Australia. She was also a visiting researcher at Max Planck Institute for Quantum Optics, Germany, and worked with Professor Ted Hens, a Nobel laureate in physics. Professor Chormaic founded the Quantum Optics Group at Cork Institute of Technology, Ireland. She has she has also holds position as academic member at Tyndall National Institute, Ireland, lecturer at University College Cork, visiting fellow at QCitec Macquarie University, Sydney, CNRS visiting researcher at Laboratory Annie Cotton University, Paris North, and a visiting researcher at Nano Optics and Force Group Institute, Lille, France. So now I would like to deliver this forum to Mr. Chormaic, to Professor Chormaic.
Okay, thank you. Can you hear me?
Yes, ma'am, we can hear you.
Okay, so I'm going to share my screen very slowly this time because the last time it crashed. So I'm going to check to make sure it doesn't crash this time. So can you stop sharing first? Because the sharing, I think that might be the problem.
Yes, ma'am. Yes, ma'am.
Okay, so if you stop sharing.
Wait, ma'am. Okay, ma'am. Now you can share.
Okay, now I try again, and let's just see what happens. Can you see my screen?
Yes, ma'am.
And you can hear me?
Yes, ma'am. Yes, ma'am.
Okay, so it all seems to be working okay, because I've repeated it multiple times to find the conditions to get it to work. So I'm very sorry for anyone who is listening, has come for the second time. I also have my email open today so that if something does happen that I'm emailed and I'm aware that it has stopped working.
Thank you, ma'am.
So hopefully now it should be okay.
Yeah,
so I'd like to thank the students for inviting me to give this talk to all of you in Guwahati. I was originally supposed to visit in May, but then obviously due to COVID-19, I had to cancel my trip to India. And since then, more or less not allowed outside of Japan. So giving some online talks, hopefully that's some way helpful, but it's obviously not equivalent. So I'm going to talk about some of our research work using very thin optical fibers and just show you some of the different areas that these can be used in. So I'm not going to go very deeply into any of them because I know that the students come from many, many different backgrounds. So I hope that some of you will have interest in some of the different topics I show, even if it's just in the optical fibers themselves, because it's the optical fiber which is the main device behind what I'm talking about. So just to let you know about where OIST is, so we're located in Okinawa. And Okinawa, there's an island chain south of Japan. So here's Japan as everybody knows it. This is a subtropical island chain, so still very, very warm. I think the climate is quite similar to sort of Bangalore in India, although it's at the coast, so some variations. And we're very close to Taiwan, so the island chain goes all the way down towards Taiwan. And the university is located on the main island. and it's quite a new university, so many of you possibly haven't heard of it, although we have had some students from GUWAHATI coming here for internships. And it's always expanding because it's a new university. If you look at our website and you think, oh, I'm not interested in what they do, every year we add maybe about 10 new research areas to the university. So it's worth checking back and seeing what changes we make fairly regularly to see what topics are available. This is a very recent photograph I just took coming into work the other day. So here's the East China Sea. This is Lab 2, where I'm located and where my laboratories are located. So that's an introduction to OIST. So please check out our website if you're interested in maybe becoming a student, whether it's for short-term internship or visiting student, or even considering PhD somewhere overseas. It is English language, just in case you're worried about Japanese. So what do? I lead a group of people, about 25 people, and it's called the Light Matter Interactions for Quantum Technologies unit. So mainly we're looking at light matter interactions. Quantum technologies I added on recently because I realized that we need to have a more defined focus. So if we can contribute to quantum technologies, that's good. So one of the areas we work in is looking at atomic systems. So we take either room temperature atoms or very cold atoms using laser cooling and put one of these very thin fibers through it and do certain atomic excitations and probing of the atoms using the light from the fiber. We also do similar using larger particles. So for example, nanoparticles or microparticles. We take a droplet of material and put these fibers through and look at how the light interacts with the particles. We also can look at light in confined geometries. So this is an example of some plasmonic type structures that we have. We have these arrays of gold rings and disks. And we look at when we shine light through these, we can do some electric field enhancement because of plasmonic features. And we can do some particle trapping. So these little beads here are indicating nanoparticles that can get trapped in various positions along these gold arrays. Another type of confined geometry we talk about is the whispering gallery resonator. So these are spherical geometry resonators. And again, we use an optical fiber for these sort of resonators to couple light into them. We don't use the fibers in plasmonics. The fiber itself provides us with the light confinement. We look at complex spatial profiles sometimes. So a normal laser beam has a Gaussian profile, so most of the light intensity is in the center of the beam. But sometimes we change that to look at what's known as donut modes. However, when I'm talking today, I'm going to always talk about the fundamental mode in the fiber. So it's like a Gaussian beam that we would project into the fiber. And finally, the more applied area that we look at is using light as a sensing platform. So it can be in one of these types of systems, or it can be in something independent. For example, we can put fibers, not thin fibers, but reasonably thin fibers, not ultra thin, into mouse brain and look at neuronal activity. And then also very different, we use optical tweezers, so trapping particles using light in order to look at plastic distribution within the oceans around Okinawa. So in this way, we can identify which are the main plastic pollutants in the seas around us. So we have quite a variety of topics in the group, from very fundamental in atomic physics down to very applied with particle identification. And what I'm going to talk about today are examples of atoms, example of particle trapping, and example of these whispering gallery modes. So I know the title of your series is Optics is not just about optics anymore. So I think you can see with the scale of work that we do, I've had students, I've just graduated a PhD student last week in environmental science because of this work. I've graduated a student earlier this year, about 8-10 months ago, in biomechanical engineering for this work. And I also currently have a chemistry student. So this is one of the unique things about OIST. Even though I'm a physicist and the basis behind our work is physics, students are free to move from one field into another as long as they're motivated enough. So I, as a physicist, can supervise a student in a topic and bring them to PhD level, as long as there's a synergy between what they want to study and what I have available in my lab, which is obviously, being an optics lab, a lot of lasers. So I'll introduce you first to the ultra-thin optical fibres. So what are these very thin fibres? Well, most of you will be familiar by now with the concept of a normal optical fibre. So a normal optical fibre is used to bring you the internet so that you can watch Netflix. If you're lucky, it comes to your dorm. If you're not so lucky, your Netflix probably isn't so good. And these are normal fibres. And what we do in our work is we consider one of these normal fibres and we adapt it. So a normal fibre has two core elements that allow you to guide light through it. So one of these is actually called the core, and then you have a cladding. And typically both of these materials are made from silica, SiO2, and within the core you will have some dopants. And the dopants mean that the refractive index of the core is going to be slightly higher than the refractive index of the cladding. So if I just slice through that fibre and look at half of it and look at the refractive index profile, I have a very slight difference between, as I go through the cladding up into the core and down to the cladding again. So you can see typical numbers of refractive index here. So a very small change between them. But this change is what allows the light to propagate through the fibre. So essentially, if I think of a ray picture of light propagation, the light enters the fibre and then reflects at each boundary. And each time it reflects, it's due to this refractive index difference. But there's one feature that we don't think of when we're looking at this, and that's at the boundary where you have the reflection, you also have some light escaping. And this is light in the form of an evanescent field. So it's not a propagating field, it's decaying from the surface of the fibre into the cladding. But the whole system is designed, because of these refractive indexes being so close to each other, that the evanescent field extends minimally into the cladding. So it's not really something we're concerned about. And you just have your light, you view that you put light into the core and it comes out the other end. So this is just showing a model of where the light energy is. So if we talk about a single mode fibre, that means only one type of optical mode will propagate, which is called the fundamental mode. So your maximum intensity is in the middle of your fibre. And in order to solve this mathematically, you solve Maxwell's equations and you apply some approximations, and then the modes are called linearly polarized. So this again is an approximation, but it's perfectly good for normal optical fibre that you see all the time in Christmas decorations, maybe Diwali decorations, anything like this that's using optical fibre. But for us, the situation is quite different. So we're interested in very thin fibres. So in these very thin fibres, I start off with normal fibre. So I just take a piece of normal fibre and I apply a heat source to some region and I gently pull the fibre. So it's getting thinner and thinner where I'm applying the heat source. And essentially it gets so thin that the core material becomes negligible. Okay, so this has gone down, reduced in size by a factor of about 100. And the cladding material which surrounds the core gets down to sizes of sub-micron, so about 1 micron or less. Now, what we have is, if you just think naively of this, I earlier said that the difference between the core and the cladding allows my light to propagate through the fibre. And now I'm saying, well, I've got rid of my core and I only have cladding. So how will light propagate? Well, it still can. The environment around the fibre now acts as a new refractive index material. So we now have a very big change in the refractive index. Instead of this change, we have the change between the silica material and whatever is surrounding it, whether that's air, whether it's water, whether it's ethanol. So depending on what you want to put here, you're going to be able to play with your refractive index. By playing with this refractive index, we're also playing with how much of the light extends in the evanescent field and how far it'll extend into the evanescent field. So now we have a region. We have light coupling into my fibre. That light will couple out of my fibre, but in this waist region, I can have a really huge interaction with the guided light through the evanescent field. So if I just look schematically and look at how the modes look, so this would be similar to what I showed on the last slide. A normal optical fibre, most of the energy is confined within the fibre, have a small leakage of evanescent field. As I make that fibre smaller and smaller, the leak becomes larger and larger, and then I can enter a regime where the waveguide is so small compared to the wavelength of light propagating through it that the evanescent field becomes high and it becomes stronger than what's in the core. Now, in this picture of the evanescent field, you can see some structure. So that's indicating we have linear polarized light. If I had circular polarized light, I wouldn't be able to see this structure. I would just see a large evanescent field surrounding the entire fibre. Okay, so what do we have? We have a system with light being guided, but still able to do an interaction. And the other advantage that we have over a free space optical beam is that the region where the light is escaping into this evanescent field is several millimeters long. Okay, so if I want to do these experiments, if I want to have this light confined into a really small space, and if I go to any undergraduate lab and I tell a student, I want a light beam that's only 1 micron in diameter, the average student will pick up a lens and try to focus the light down to 1 micron in diameter. And that's fine, it's perfectly okay. The problem is if you try to focus light to 1 micron, you'll only get it focused over a few micron at best, depending on your wavelength. So your interaction length when you focus light is only going to be a couple of micron. For the ultra thin fibers, I focused the light to the size of my fiber, and my interaction length is several millimeters, and it can be up to 1 centimeter. So what I've essentially done from an optics point of view is I've broken this Rayleigh limit, so which tells me how tightly I can focus a light beam and over what length that beam will act like a focus beam. So I have a long interaction region and I have high intensity fields in my evanescent field. And these are the features that we exploit. So here's how I make one, okay? This is a fancy way of making one. I can actually make one quite easily. I just need 2 people, but in this case, the 2 people are these clamps. This is one person's hands. The other person is holding a flame, and you scan the flame across the fiber. And while you're scanning the flame, you gently pull the fiber so that's getting elongated. And this creates the nanofiber. So the speed at which you pull here will tell you how long the nanofiber region will be. The flame here is being scanned to make sure we're not breaking it, because you can imagine if you're heating something and pulling it, you might just be concentrating the heat in too narrow a region. So this is really controlled with a certain algorithm to ensure that the light that we put in through the fiber will not be lost, okay? That it'll just go into the evanescent field, then recouple out the other end of the fiber. So what does a typical fiber look like? Well, these are nanofibers, a few hundred nanometers in diameter, maybe 1 micron in diameter. You can't really see it. So the way you can see it is make it dirty. So if I put dust on the fiber, like you see here, and I propagate light through the fiber, everywhere there is a dust particle, it acts like a scatterer on my fiber. So essentially, this is a bad fiber because by the time I put light in at the left, very little will come out at the right because it's been scattered and lost all along here. So while this is bad, it also is good to have one single scattering point. And the reason to have one single scattering point is that allows me to determine the polarization of my light. So you have a fine balance between having essentially no dust, but one point on your fiber where there is some scattering happening. So this could be an atom, it could be a dust particle or whatever. So what do I think of these fibers? Well, I think because I never have to make them, that they're relatively easy to make. So any student coming through my lab, the first few weeks will be spent making sure they know how to make a nano or a microfiber. The other things are, this evanescent field is extremely intense. So if you think of how much we're focusing that light down, we're starting off with a fiber where the core is, I don't know, maybe 9 micron, and we're focusing it down into a few hundred nanometers. And the intensity is inversely proportional to the diameter of the beam. So as I make the diameter smaller and smaller, I'm getting higher and higher intensity. And this opens up a lot of nonlinear optics features for me. It's a fiber. Okay, a fiber means that we can easily move it around where we want it to. We can tie it in knots, and it's very, very stable. So despite the fact that this is only a couple of 100 nanometers in width, if there's a tensile strain essentially on it, it doesn't snap. Okay, so this is due to some of the features of glass. When glass is this small, a lot of the cracks simply cannot form because there isn't the space and the crystalline structure for these cracks to form. The other thing is, which is really important, is that we can easily connect the fiber to anything else that's fibered in the lab. And what this means, if I'm looking at quantum technologies, that we have very low loss. So we're not playing with things, trying to connect something or trying to force something to connect into our fiber. It's immediately fibered. Okay, so now some of the applications that you can have for these fibers, and there are many. Okay, so starting off down at the bottom of this tree, this was essentially at the beginning when people were doing research into it. They were looking at the evanescent fields. This adiabatic transition is to ensure that they're effectively lossless at 100% transmission. People started to do particle manipulation with the fibers. People started to use them for making cavities. As I said, they're fibers. You can loop them, you can knot them and make cavities this way. You can exploit the non-linear properties of the glass material itself because of the fact you've such high intensities within the glass, not just outside the glass in the evanescent field. You can use them for generating supercontinuum. You can use them to make an atom trap. So instead of a normal magneto-optical trap, you can get nice one-dimensional atom traps along the fibers. They can be used as sensing devices. So they're extremely thin. So the slightest thing, one particle coming near it, and you can get a change in your intensity of light. And many, many other areas, okay? So some of the things that we look at plasmonics. We can coat these fibers with plasmonic structures. We look at optomechanics. So the photon momentum passing through these fibers can transfer to a particle near the fiber. Waveguide near field optics, it's obvious because they are waveguides in themselves that you can use them as waveguides or as near field coupling devices into other optics elements. Microfiber gratings, we can take one of these fibers and do further processing, so take a focused ion beam and cut holes in the very thin region and make really nice bright gratings along them. Microcavities, very similar, a technique similar to the microfiber gratings. Other components that are passive, this main one here is the optical coupler. So if I have this evanescent field outside the fiber, imagine this my fiber, and I bring any optical component up to it, I can get light coupled into the optical component. And quantum and atom optics, so this would be similar, as I said, you can have traps around them, but not only that, you can use them for designing quantum networks, looking at chiral behavior from atoms. So I'm going to show you 3 applications, and I said I hope that the applications somehow appeal to the audience. I've tried to make them as visual as I can. The first one is a passive device, so I'm going to use the fiber to couple into a whispering gallery resonator. So what is a whispering gallery resonator, first of all? They're spherical geometry, typically silica or some other glass, little devices, tens of micron in diameter. and they're cavities. So when you manage to couple photons in here, the photons will propagate around the equator in an optical mode, and they will propagate for a very long time. So the optical path is huge. So again, if I put a photon in here, that photon will keep propagating around. There'll be some losses due to scattering, but essentially the propagation distance could be of the order of kilometers for the photon, even though the device is only micron sized. So where did the name come from? Well, it actually came from St. Paul's Cathedral in London, but you also have an example of a whispering gallery in India. And of the whispering galleries I've been to, which is St. Paul's Cathedral and the Temple of Heaven in Beijing, the Temple of Heaven in Beijing is fantastic. So it's huge. The wall is actually the whispering gallery, not the temple itself, but this wall in the background. If somebody stands on one side and whispers very quietly, you can hear this whisper on the other side. I've never been here to Bijapur. I understand this features or used to feature in school books in India in some areas, and that the school book said you don't whisper, you shout. And of course, that means that you can't hear the whispering gallery because everyone in there is shouting, trying to hear the effect. And once you shout, you don't hear the effect because you just hear normal shout, normal voice carry. So the way this actual carries and why it's called a whispering gallery, you can view this as multiple reflections of the photon, so similar to what would happen to an acoustic wave. The sort of devices we use are bubbles and microspheres. So I'm just going to talk about bubbles today. Here you can see one of these very thin fibers. So this fiber, imagine the light is coming from the top down past the cavity. The light then couples into the cavity, circulates in the way in the little cartoon at the top, and then couples back out of the cavity. This is a micro bubble, so it's hollow, so I can fill it with something, and then I can have an interaction between the light in the cavity and whatever is inside the cavity. Okay, so the fiber is just acting as a coupler and nothing else, and it's allowing us to determine whether the cavity resonance shifts or not. Okay, so cavity resonance, if we think of this picture here, it tells me how many wavelengths of light can fit within it. So if my cavity gets bigger, I can fit more wavelengths. If my cavity gets smaller, I can fit fewer. And if each cavity will have a number of resonances, so these resonances for the cavities are what's called the whispering galleries or the whispering gallery modes. In this example here, the bubble is closed at one end, okay, so it's made from a capillary. Bubble is closed, so once I fill it, it's almost impossible to get the liquid out. But there are different designs of bubbles we can make. Here's a video making the bubble. The big thing at the bottom is just some optics. Here's the bubble forming. So I take a capillary, I blow into the capillary, and I shine a CO2 laser on it as a heat source. So it's just like miniature glass blowing. If you've ever seen somebody blowing a vase or a glass using molten glass, it's the very same technique. So you blow through it while heating it. And these have about 80 micron, 100 micron in diameter. Now the walls of these bubbles are extremely thin. So how do we know that? Well, we break the bubble, okay? So it's a destructive measurement method. So we just break the bubble, grind it down to try and make it smooth, but it's a glass material, so there is some shattering. And then we look at using the scanning electron microscope, we measure this thickness of the wall, and it's usually less than 1 micron. So if the bubble wall is less than 1 micron, an interesting feature happens. If I couple light in so that it's propagating around the equator, most of that light energy will actually be carried in the medium inside. So the glass wall is too thin to carry the optical mode. So this is how I can do sensing using these devices. So I fill my bubble with some material, and then the optical mode gets pulled into that material by having a very thin wall. You can have other designs, okay? So this is a system where you'd have 3 different bubbles. They're all going to be slightly different sizes. So you can imagine you would have slightly different resonances with each of these cavities, So that means you'd have a slightly different wavelength, would match with each cavity. And if you put, for example, let's imagine some type of dye particle or nanoparticle through here, and each one interacts with a certain wavelength, you could maybe imagine that you could do sensing of different types of nanoparticles in each of these bubbles. Okay, so the example of the experiment I'll show you is going to be nanoparticle trapping. So I take one of these bubbles, and this one is open, so I use fluidics to flow water through here, and within the water I put my nanoparticles. These nanoparticles can be anywhere around 500 nanometers, 200 nanometers, 100 nanometers in size. If one of these nanoparticles comes close to the bubble wall, it's like the bubble wall gets a bit thicker, okay? So you have this change in the resonance. I use this light beam here, which is going through my optical fiber to monitor my resonances or my whispering gallery modes. And I use another laser beam. Sorry? I use another laser beam to pump the nanoparticles. So 532 nanometers pumps the nanoparticles, and 630 nanometers is the emission. So I can monitor the emission of my nanoparticles through my lens here, or I can monitor the shift in my modes as a particle comes close to the wall or moves away from the wall. So just some of the experimental parameters. Microbubble diameter about 100 micron, wall thickness about 800 nanometers. The particles that I'm going to show you are 500 nanometers. 780 nanometer laser we use just to monitor whether the particles are present or not. Fiber diameter is somewhere in this region, depends on which fiber I do. And how good is this as a cavity? We measure the cavity using what's called the quality factor, and this tells us about the width of the resonance. So again, it's related to how long a photon or a particle of light will propagate around that cavity. When there's nothing in the cavity, it's very high, 5 by 10 to the 7. When I fill the cavity, it drops by a factor of 10, but this is still an excellent cavity. And I do my experiment. So here you can just about see the bubble outline. Liquid is flowing from the top to the bottom. Here you have a scattering point, so my fiber is just going along horizontally like here. And you'll start seeing when I turn it on, you can see particles scattering light. So these are particles flowing from the top to the bottom. And when they feel the interaction from the evanescent field inside the fluid, they get captured by the optical mode. So you have an optical force that pulls them into the optical mode, and then they start circulating in the optical mode. So you can see the particles are going around in circles in various positions, and this is the mode of a bubble. So the mode of one of these bubbles circulates like a spiral through the bubble, then hits a turning point and circulates back. And remember, it's the glass that guides the mode, similar to my fibers, but the actual energy of the mode is mainly inside in the fluid in the material. And this line here, where particles are most likely to be trapped, is where my fiber is coupling my probing light in. So two things I can look at: scattered light or the light through the fiber. So the scattered light, you can see these very nice signal peaks. So these are my resonances as the particle comes into view or out of view. So it's oscillating around in time. And we can see then the frequency of my rotations. The transmitted light is through the fiber, so you can't really see the variations here. And the reason why we can't really see much in our transmitted light is that to do this optical trapping or optical capturing of the particles, we need a lot of light energy. So we have to use a lot of power, and everything heats up and just gets some washing out of the signal. But with this scattered light signal here, when the particle is in front of my detector and so on, I get these massive spikes. And from this, I can determine how quickly the particles move. And we can see that the speed of the particles is of the order of about 1 millimeter per second, and the rotation frequency of the particles is about 6 hertz. So I can increase these by increasing the pump power. So if I give more and more energy into the fiber, more and more energy will couple into my bubble resonator, higher trapping or capturing optical force on the particle, more momentum transfer on the particle, which makes it rotate even faster. We can look at some different types of bubbles and the features that they give. So here you can see a particle coming in from the top. Again, you can just about see the fiber coupling the light in. The particles, as they come in the top, get captured by the optical mode and then start speeding up as they're getting closer and closer to where the fiber is. That's where you'll have the maximum intensity. On the next one, it's so fast you won't be able to see it. It's the highest rotation speed that we've managed to achieve, which is 300 hertz. So you just see a smearing out on the camera. We don't have a very fast camera for looking at this. And then the last video really shows you these nice caustics for the bubble mode. So these are the turning points. So in this video, we have particles captured in the turning points and various positions along the optical mode. So we know that we can capture the particles using the optical mode, but considering the speed at which they're moving, it's very hard to do anything with them. So what we now need to do is, instead of capturing it and allowing it to go along the mode, we want to trap it in one position. So the obvious thing to do is consider putting light in two directions. And then no matter which way the particle moves, it'll be trapped and confined in space. So for this, instead of putting light in one direction of the fiber, which causes a rotation in one direction around the cavity, we put light in two directions, and this couples in two opposite directions into the cavity. So I just show you a video of this. So here's the technique. So we put light in, we have the capture, we turn on our second light, and then you start seeing that the particles are no longer moving, they're trapped. So in a second now, you're going to see one of the trapped particles coming into focus as the light is being switched on and off. At the moment, the light is off. Now the light is on. So this new particle got trapped. Okay. So once the particles are trapped, you can then do very nice spectroscopic studies on them. So we work with chemists in the US in order to fully characterize the spectroscopic behavior of metallic nanoparticles within these bubbles. So the second application I'll talk about is optical binding and angular momentum. And in this application, we only use the fiber. So we don't use any cavity to enhance the optical features. So many of you will know optical tweezers, where you use a very tightly focused beam, and then you have a gradient force and a scattering force from the optical field. And this captures beads in certain positions. So here we have an optical tweezers. The optical tweezers moves the beam around in this pattern so quickly that little particles get trapped each point, and it goes back to the original place before the particles can escape. This nice little heart-shaped optical tweezers was built very late one night in my laboratory. So my postdoc was working, and it was his wife's birthday, and it was 3 a.m. and she was not happy that he was still in the lab. So he tried to keep her happy by sending her an optical tweezers of a love heart. So I'm not sure if that was enough for her birthday, but that's what he gave her. So similar to the optical tweezers, which is using a tightly focused beam, we can capture the particles just using the fiber. We don't need an additional cavity. So here we have a fiber, and we pass light from left to right through the fiber. And you can see these little polystyrene spheres, little beads getting pushed along the fiber. So what's happening is you've got the evanescent field extending into the liquid environment of the particles. Some of the particles get captured due to the gradient force from the evanescent field. They get pulled towards the optical fiber. You then have a microfluidics effect, which lifts the particle about 20 nanometers from the surface of the fiber so it doesn't stick. And the momentum from the laser beam light gets transferred to the particles, and they just get pushed along by the beam of light. So again, some of the advantages, of course, is that we now have a fiber system, so we can make those particles go wherever our imagination brings us to and wherever we can put a fiber. We need a fluidic system, but it really opens up some opportunities compared to the optical tweezers. The other feature that we can look at very nicely in this system is the angular momentum of light. So if I think of the polarization of light, which provides a spin on a particle, it's a spin angular momentum. How would the spin angular momentum of light transfer into the particle motion? So what would be the optomechanical effect that we could imagine in that situation? So these are the sort of experiments we do here. We have an optical tweezers. We capture particles using the tightly focused optical tweezers beam. We then bring them next to the nanofiber, turn off the optical tweezers, and then turn on the nanofiber light and look at what happens. And what we can do is we can work with chains of particles, depending on how patient the student is. So this one is a chain of 4 particles. I think the maximum we've managed to do is a chain of 7 or 9 particles, where we can look at these interactions. And I'll show you a video of the sort of behavior we get. So these are the particles already released next to the optical fiber. We have light going in from the left to the right. And when the chain of particles arrives, you'll see that the spacing between the particles is not uniform. Okay? If I take one particle, if I pull one particle out of that chain, those particles will redistribute themselves, and we can fully theoretically model the distribution of the particles. So what happens is that the light that's going through the fiber gets scattered also off each of these particles, and this creates little optical minima around where each particle can be captured. Another feature that we can look at, and this is the only point where I'm going to talk about higher order modes, is the fundamental mode is sort of the Gaussian beam that I'm propagating into my fiber. A higher order mode has a more complex structure. So this can be a beam where most of the intensity is in the outside. And then when I couple that into the fiber, it also gives a longer evanescent field. Okay, so the fundamental mode will give us some evanescent field. The higher order mode will give us a longer evanescent field. But the higher order modes can also contain some interesting optical features, such as angular momentum, that the fundamental mode can't. So here we'll just look at very basic linear momentum transfer, fundamental mode versus higher mode. Okay, we're putting in the same type of power into each, and you can see that the higher order mode particle moves much faster than the fundamental mode, and about 8 times faster in these videos. So this is showing us that the momentum transfer for linear modes, even though I have the same power, is significantly higher if I go to a higher order mode. So again, for higher order mode, that means that more of the energy must be in the evanescent field than the fundamental mode. And then the final feature we can look at with this is the angular momentum. So there are 2 types of angular momentum for light. There's the orbital angular momentum, which causes a rotation of the wavefronts of the light. And there's the spin angular momentum, which is a rotation of the electric field. And this is the polarization of light, the spin. So in a normal free space beam, these 2 types of angular momentum are very different, okay? And the behavior that they have, or if I shine a light beam with orbital angular momentum or with polarization on a particle in an optical tweezers, I will get very different behavior. The polarization will just spin the particle around itself. The orbital angular momentum will create the particle to follow an orbital track. So similar to what they call a satellite. So it'll just do some form of orbital track. And that's for a free space beam. But remember, I don't have a free space beam. I've got like equivalent to a highly focused beam going through the fiber. So it's a non-paraxial approximation. So I cannot make all these approximations we do in undergraduate optics. So I have to consider this fact that it's a non-paraxial beam. And what does that mean for the polarization of light? And it becomes a very different scenario. So in the polarization of light, when I have a non-paraxial beam, I end up with transverse spin components. And these transverse spin components can be transferred or transduced into orbital motion of the particle. So to get orbital motion of a particle in a non-paraxial beam, I do not need orbital angular momentum. So this project started because we wanted to look at orbital angular momentum. And then in the last few years, there's been a lot of study on this, the difference for non-paraxial beams, and it actually made it simpler for us because we only have to play with the polarization. So what we do is we take one of these fibers, we define the polarization, which is sigma. K is just telling us the direction of my beam or the direction of my wave vector. Sigma is telling me the orientation of my circular polarization in the experiment. And I use a quarter wave plate so that I can vary the polarization of one beam. And what I want to look at is this spin orbit coupling feature. So the spin of the light will transfer into an orbit of the particle around the fiber. And again, the easiest way to see this is through a video. Here, my two beams, the power isn't balanced, so the particle is being pushed from left to right, but you can see the rotation of the particle around the fiber. And if I look at how this rotation changes, so the frequency of the rotation as I play with the polarization in my beams. So I just change the polarization, rotating my quarter wave plate. I can see that the frequency goes through maxima for a certain polarization, and that's where I'd have circular polarization, and goes through zero where I have linear polarization. So I wouldn't expect any rotation if I have linear polarization in the system, and indeed, I don't see any polarization at these points, which are linear light. I can look at how that frequency changes with the power, and as you can imagine, it increases linearly with power. But this wasn't such a great experiment, okay? You can see the particle is being pushed as well. So we did some improvement. We introduced what we call a polarization compensator. So I mentioned right at the beginning of the talk that if we have a scatterer here, I can monitor the polarization. So we essentially use the particle as a scatterer, look at the light that's scattered. From the scattered light, we can determine the polarization at the waist. If it's not the polarization we want, we do a feedback process, readjust the polarization using the polarization compensator, and then I rotate my quarter wave plate, and I've one in each beam now in order to optimize my signal. So if I look at the sort of videos I now get, much slower rotation, much cleaner rotation, less motion along the fiber, so I'm getting better balance between my two beams, between the linear momentum on my two light beams, and here's where I have a full balance beam, spin angular momentum, very obvious. And again, we can plot the frequency of our particle rotation as a function of the quarter wave plate. This just is having a detector here. Looking through this objective lens, we can look at when we have the particle in front of the fiber, it gives maximum scattering. When it's behind the fiber, it gives low scattering. And the thing that we observed is that the orbit direction is opposite to the direction of the circular polarization. Okay, so it's not just that we're spinning the particle, it really provides us with a negative torque on the particle. And here are some, if we bring in two particles, how they start moving in unison, okay? So they completely couple together and dance like a nice partnership, essentially. Okay, so then the third topic that I'll go into just briefly is an example using the fibers for cold atoms, so in atomic physics. So again, we have one of these fibers and we can bring a quantum emitter next to the fiber. If it's a quantum emitter, light can couple from the emitter into the fiber and we can do photon statistics. Or we can pass light through the fiber. That light is on resonance, for example, with atoms, will be absorbed by the atoms, and then we can see the decrease in our signal because of whatever is absorbed here. So I'll talk about this type where we have an active behavior. So in the very first example, which is passive, you don't do anything, you just let your atoms sit there. So here's an example of an atom cloud. This is just showing you where the fiber goes through the system. We have maximum light coupled into the fiber when we have cold atoms. So if we turn on the magnetic field for our laser cooling system, we get most scattering. we turn off the field, we get very little scattering. So that's about all you can do with passive detection. If we do active, a very common example is fiber-based traps. So our atom will have a certain atomic transition, and if we move to blue wavelengths or red wavelengths from that transition, we can do what's called two-color trapping. So the red light passing through the fiber pulls atoms towards the fiber, and the blue light passing through the fiber pushes those atoms slightly away. So you've got a pulling and a pushing behavior on the atom, and the atom ends up in some equilibrium position around the fiber a few hundred nanometers from the surface. So these are called fiber-based dipole traps, and they've been realized in many labs, and we also do some experiments on this in our lab. So what you end up with is a few hundred atoms in a line along your nanofiber. And these are the sort of optical potentials that you can get. So you typically use linearly polarized light in these experiments, and then the atoms, you have a standing wave, and the atoms just distribute themselves along this standing wave. So what we look at are Rydberg atoms. So instead of normal cold atoms, we look at highly excited atoms. And these highly excited atoms have some features which are very nice for quantum information. So in these Rydberg atoms, how do I make them, first of all? Well, I start off with an atom in a ground state, and I apply certain laser energy to make the atom very excited, and the outer electron gets excited to a Rydberg level. So R here is a Rydberg level. This omega here tells me about the Rabi frequency. So essentially it's telling me the intensity of light I need to apply in order to be able to get this transition. So in order to be able to reach the Rydberg state that I want. And the Rydberg state that I look at is typically n equals 30. So instead of a ground state atom, I'm going to a highly excited state. If I bring two atoms close to each other and they are in Rydberg states, they will interact and they create a van der Waals interaction. And this shifts the resonance between those two atoms. So essentially this feature where I have two atoms interacting with each other means that I cannot bring them too close, or essentially one of them will not exist. It will not be a Rydberg atom. And this is a feature that's used for quantum information. So if I just think of a very simple thing, instead of the energy level diagram, the green dots represent my ground state atoms. The red represents a Rydberg or a highly excited atom. I cannot, when I shine my laser beam on my normal ground state atoms, as soon as one Rydberg is created, within a certain volume of space, I cannot create another Rydberg atom. So the next Rydberg atom will have to be a minimum distance away. It can be far away, but it cannot get right next to it. And these little blue circles then, which are surrounding the ground state plus Rydberg, we call this a superatom. So the superatom consists of the ground state atoms, which can be 1,000, 10,000 ground state atoms, and one single Rydberg atom. And each of this can create a qubit for quantum information, where one bit represents the ground state and the other is the excited state. So these have been used for quantum information in experiments and so on. But one of the problems is that nothing is fibered, and in order to have high efficiency, you need to be able to do everything through fiber. So what we want to do is have these atoms, ground state, laser cool them next to the nanofiber, and try to create Rydberg atoms. Now, Rydberg atom is a very large atom. The Rydberg atoms we work with are about 50 nanometers in size. So remember, this fiber is only a few hundred nanometers. So at some point, are we going to have a case where the atom becomes larger than the fiber? And that would be extremely interesting. But first, we need to know, can we make the Rydberg? So to make the Rydberg, we have to do a 2-photon transition, or else we'd need an ultraviolet laser. So we just have a probe laser and a 482 with blue laser. This is used to cool our atoms and do the first Rydberg excitation, and the blue is to create the highly excited Rydberg atom. The blue light goes through the fiber, okay, as you can see here. The 780 nanometer light is always present. This is just our laser cooling. And then we have an additional beam of 1064, which is an atom trap. So one of these fiber traps, which pulls atoms closer to our fiber, essentially increases our signal. And what do we see? So we create our cold atom cloud. We turn on our cooling lasers, our magnetic field. We reach some saturation level. And then we turn on our Rydberg laser. We lose atoms from our cold atom cloud. So these atoms that we lose might be ionized or they might be Rydberg atoms. So we do some studies to see where do those lost atoms go. So we have a simple equation which shows the exponential increase of atoms in our MOT. So the number of atoms in our MOT is just an exponential increase, and the decay is just an exponential decay. And within our decay, we have some total loss, and some of that loss is due to the mass, the MOT loss from the atoms overall, and some is into the Rydberg system. So what we want to do is scan the frequency of this laser to stay on transition around our Rydberg. And if we have Rydberg, we should see a resonance. So if we scan the transition and we look at essentially the loss or the decay rate of our MOT, we see no change. So the decay rate of our MOT, that's purely a decay, nothing that we can have, nothing of interest. If we look at the gamma R, so the decay into Rydberg component, we start seeing very clear signals. Now the red and the black, don't worry, that's just two different transitions. One is to 29D 3/2, so two transitions within the atomic structure. 0 is our resonance. We have signals to the left and to the right of our resonance. These are two different processes where we're generating Rydberg atoms. So you can see a small difference here. This is a 2-photon process, and this is a standard stepwise process. Okay, so here the delta represents our detuning, okay, from our original transition. So here delta we don't really have because our blue laser is detuned in order to cover it. So it's a 2-step process, whereas this is a 2-photon process. So we clearly have Rydberg, okay, we've seen good verification of Rydberg. And one of the main interesting features of this is we have a Rydberg atom next to a dielectric. So a dielectric is a highly charged surface. A Rydberg atom is can be a highly charged atom, so it can be easily ionized. And up until now, if people wanted to bring Rydberg atoms near dielectric materials, they could only come around 10 micron from the surface. But what we have here from our theory, we're about 100 nanometers from our dielectric surface. And we have a fibered Rydberg system. So now what we want to do is try to see, instead of just going to 29 level, can we go to n equals 50? Can we go to n equals 100? And it's when we get to n equals 50 and n equals 100 or anywhere up that high that this Rydberg blockade feature starts becoming very important. The other problem with, as we go to higher n value, the atom is easier and easier to ionize. So what we need to discover is what is the limitation of Rydberg before they get ionized by our system. So that's essentially the next study that we need to do there. So what I've talked to you about are 3 very different experiments, all 3 relying on ultra-thin optical fibers. I hope that they'll show you some of the range of experiments that can be done with these fibers. Some of them more applied, where the fiber is really just acting as a device for the whispering gallery work. But other ones like the cold atoms and the particle manipulation and trapping along the fiber, it's really without the fiber, we simply couldn't do these experiments. So hopefully you'll appreciate ultra-thin fibers a little bit from this talk. So the things I talked about, 2-photon processes in cold atoms. Things I didn't talk about were these cavities that we can make on the fibers. So I've mentioned it in the first couple of slides. And what we're doing with these cavities is we're looking at cavity QED. So we're bringing quantum dots into this cavity that we have on the fiber and seeing whether we can reach strong coupling. I very briefly talked about the higher modes. I just showed you one video where particles were moving very, very quickly. But another feature of higher order modes is that they contain orbital angular momentum. So we talked about spin angular momentum and transferring the spin angular momentum to the orbital motion of a particle. But we could also look at what is the orbital angular momentum of light doing in this non-paraxial regime. I don't do the work, of course, I can't do all of this. So this is my team. These are the countries where they come from, and these are the places that give us money. So I would like to thank you for listening.
Thank you, ma'am.
Thank you,
It was
ma'am.
a very informative. It was a very informative talk, and now I invite questions from the audience. Anyone has a question can unmute himself and ask a question. Anyone in the audience has a question? Okay, ma'am. We have some. Okay.
Yeah.
Okay, Rajkumar Thakur.
Thank you so much, ma'am.
Okay. Yeah. You have a question?
Okay, ma'am. We have a question.
Yeah.
Okay,
Yeah.
Yeah. With regard to the 3D cold atom experiment, you said,
Yeah.
what is the physical significance behind why the transmission signal is not symmetrical when the magnetic field is on and off?
Okay, that's very easy to explain if you know laser cooling. Okay, so to do laser cooling of atoms, we need a combination of a magnetic field and lasers. The lasers cool the atoms using a transfer of momentum between the photon and the atom. The magnetic field, in combination with the laser, provides a potential which will trap the atoms in space. Okay, so when I turn on, it's called a magneto-optical trap. So it's the combination of the magnetic field and the light field that traps and cools atoms. If I turn off the magnetic field, the atoms are still being cooled, so they're getting a lower temperature, lower velocity, but they're no longer confined in space. So if I'm looking at a signal in a certain space around my fiber, the atoms are no longer confined there. They just go everywhere within my vacuum chamber. So my signal drops. Okay, then if I turn on my magnetic field, the atoms bunch up together again next to my optical nanofiber in the magnetic field where I have it optimized for the trap, and my signal increases. So all it's doing is turning on and off the trap on the atomic system. Does that answer the question?
Yes, ma'am. Yes, ma'am. Thank you,
Okay.
ma'am. Thank you.
Ma'am, there is a one more question in the chat box. He's saying that, ma'am, if by putting nanofiber in mode, single atom can be trapped. Is it also possible to generate an array of single atoms along the nanofiber? Can this also be generalized in 3D?
So the fiber, it's very hard to trap a single atom. Okay, so the way the trapping is done is using a standing wave. So I put two red detuned beams, one through either side of the fiber. Those light beams interfere in the evanescent field and they create like an egg box potential around the fiber. All right. The atoms will distribute, if they're cold enough, into one atom in each little egg box minimum. Okay. So I could end up with a few hundred atoms along the fiber. The distribution, whether it's 1D or 3D, depends on the polarization of the light. So if the polarization of the light is linear, it's like a 1D system. If the polarization of the light is circular, okay, and it won't be fully circular, but it can have a big circular component, then it'll be like rings around the fiber. So it'll be a 3D system. If I wanted a single atom, I would need to somehow empty all those potentials, all those little egg box minima, so that there's only one atom left in one box. Okay, so my feeling is, if you want a single atom, you're better off using a tightly focused laser beam, just like an optical tweezers. Okay, if you want tens of atoms, the fiber-based traps are very good.
Okay.
I think that.
Yes, ma'am. There is one more question in the chat box. He's saying that, ma'am, can you please say a few more points on how the final heart-shaped birthday gift was detected?
Yeah.
And what was the typical size of those individual dots, and how do you confirm their sizes?
Yeah, so that was the optical tweezers. So this is where you have a very tightly focused beam, okay, of about 1 micron, and it's in a fluid droplet, which has lots of particles in it. So the first way, how do I know the size of the particle? Because it's whatever I purchase and put into the droplet. So you just buy sample beads. They can be 1 micron in size, 2 micron in size, 3 micron in size. So typically that system works for about particles of about 1 micron to 3 micron, okay? Not much bigger, not much smaller. Depends on the refractive index and the material that it's made from. The refractive index of the droplet, we just use water, and the material of the particle. Now, how was the heart made? I only have a single laser beam, okay? Very, very tightly focused, 1 laser beam. But I use a very fast deflector to create whatever type of shape I want. And while my particle is trapped, if I move quick enough, I can trap more and more particles before the first particle manages to move in the liquid. Okay, so you imagine you trap something, turn off your trap, it'll take a couple of microseconds or milliseconds even for that particle to move away far enough. And if I do it quick enough, move my laser beam quick enough, I can create any pattern I want on my device. So I can use either a mirror that deflects my laser beam really, really quickly, and that's what we did, or I could use a system where I have many, many laser beams. That's more complicated. I think that answers those questions. So typical size, 1 to 3 micron. We know their size because they're big enough that we can image them anyway, but we also purchase a certain size.
Okay, ma'am. I have a question. Okay.
Mm-hmm. Yeah.
How fast these laser beams are moved on the circle or on the shape?
Yeah, so in that case, I mean, I would say, I'm trying to think of what, I would guess it's kilohertz. Okay, so again, how quickly you can move will depend on what you're using. So if you're using a spatial light modulator, or if you're using a digital mirror, or if you're using some form of piezo, that'll dictate how quickly you can move. So kilohertz sounds reasonable to me. 100 hertz, certainly fine. Yeah, no problem with any of the systems, but it will depend on what electronics you're using.
Ma'am, I have a question. You mentioned about actually a microfiber grating.
Yes.
So is this like a normal grating, and what are the advantages over the normal grating?
So there are 2 ways we can have this. So the way we look at it is we make one of our fibers, and we don't go nano, we go micro size. And we use a focused ion beam then in order to machine or make refractive index differences essentially in the material, which then creates the grating, okay? So what are the advantages over a normal grating? Well, one of the advantages, again, first of all, it's a fibered system, yeah? So it's also a tiny system. So for any form of miniaturization, there's normally a play-off between the size of your cavity and some of the features of your cavity that you want to exploit. So by making the cavity very small, things such as the intensity of your light gets very high, so you don't need to use really high-powered lasers. Heating effects can be less, okay, because you don't need, the same reason you don't have high-powered lasers. So anything miniaturization, everyone always wants to go smaller and smaller, but these are some of the more advantageous reasons. So it can be coupled to very small emitters. So we work with quantum dots. So these are about 5 nanometers in size. So for this sort of work, having the cavity also very small makes life easier. So we can sort of position the quantum dot where we want on the cavity. Does that answer your question?
Yes, ma'am. Yes, ma'am.
Okay.
Any questions from the audience? More questions?
No, sir.
Okay. So I think there is no more questions. So
Okay.
finally, we come to an end of the today's session, as well as our series of the event of this year. And on the behalf of SPIE Student Chapter IIT Guwahati, I, Akanshu Chauhan, would like to deliver the vote of thanks to one and all for making this event successful. First of all, I would like to thank Professor Shubhradeep Ghosh, HOD Physics, Department of the Physics, for inaugurating this event and for his encouraging words. I am highly thankful to our faculty advisor, Professor Tarak Natte, for his guidance and his active participation in the event. Once again, I sincerely thank our speaker, Professor Síle Chormaic, for agreeing to deliver her talk, another instance today, and sharing the interdisciplinary prospects and the applications of ultra-thin optical fiber through a wonderful presentation. Thank you, ma'am. I am sure the wide range of applications mentioned will motivate our attendees even more to pursue research and implement their ideas into the field of optics. My sincere thanks to the organizing team and all the members of the SPIE Student Chapter IIT Guwahati for their efforts and contribution. I would like to mention Rajnandan, Partha, Monu, Sampreet, Sanket, Samit, Shashi, and Deepthi for their continuous hard work in making this talks series Optics is not only about optics anymore successful. Lastly, I am thankful to the all attendees for their active participation throughout the event. Thank you, ma'am.
Thank you very
Thank you,
much.
ma'am.
Thank
Thank you,
you.
ma'am.
Bye. Bye. Have a good day. Bye.
Okay, bye, ma'am. Thank you, ma'am. And for and the feedback for the feedback link, let me share my slide.
Hello.
Hello,
Hello. Oh, sir.
yes, sir.
Just put that feedback form on the chat
Yes,
box, sir.
yes, yes,
Because
yes,
from
yes, yes,
sharing
yes.
slide, we cannot access that.
Okay, 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 okay. In the chat box.
Yes, sir.
Okay, okay, okay. So, so I'm just pasting the feedback link.
Akansu, we have already pasted the link. You can announce.
Okay. Okay, I have pasted. Okay, now I think this is the end. So now everyone can access the feedback link. Okay, so you can paste it. You can copy this link, and this is the
Sir,
end of today's event.
hello, sir.
Yes.
Sir, I'm unable to access the feedback link.
Okay, you need to copy this link. It will be activated by 11 p.m. tonight.
Okay, okay.
Okay, you need to save this. Okay,
Okay,
and
sir.
this link is also updated in our YouTube channel. In the description of our YouTube video, this link is also updated there. So if you are having any
Okay, sir.
problem, you can access from
Akansu,
there.
may I? Yeah, actually, hello. Akansu
Hello.
Rajnandan here. Yeah,
Yeah.
this feedback link is now updated, so you can just click this link and you can give your feedback. And once you give your feedback, the e-certificate will be generated within 48 hours, and it will be this link will be activated till 11:30 tonight. So kindly give your feedback, and you can directly click this link, and you will reach the web page.
Okay. I think. Okay. Now, thank you everyone for joining this event, and have a nice day. Thank you.
Thank you, sir.